All right, lesson 29, the photoelectric effect. All right, so again, remember, like the whole context of this, we're telling a story, right? Like how we got to that model of the atom. And actually, in this case, this lesson or this discovery actually turned out to be quite a big discovery as far as technology goes too. So, all right, so here's what happened. We've been doing research with cathode ray tubes, right? So we had Henrik Hertz. So the same guy, if you remember back with the uh, electromagnetic radiation lesson, for which lesson that was. But he was the one that had the experiment with the ring, right? Where he actually discovered that you could send photo or electromagnetic radiation through the air and actually induce a current in that ring that he set up, right? So the same guy. And you guys are going to find that a lot as we're going through this. It's the same set of scientists that keep making like a bunch of these discoveries. So he was doing research with cathode ray tubes because a lot of people were at the time. And what he had found though is that even after he had turned off the cathode ray tube, he would shine light on one of the sides of it, on the cathode there, and it would begin to actually send a current from one end to the other. So remember, there's like no battery actually hooked up to this thing anymore. So it was like the light rays themselves that were shining on the cathode here that were emitting electrons like to jump off of the surface here, right? And they were used to that when they were sending a current or like had like a voltage, from one end to the other. They would give it enough energy, and they understood that that was shooting electrons from one end to the other here. But this was a surprise that you could shine light on it and actually get an effect like this. And this is actually what's going to be called the photoelectric effect. Photo is another word for light, right? And then electric would be the electrons that are being emitted off of the actual plate itself. Maybe you guys are thinking about this already, but like solar panels on your house, right? They're going to use a very similar process to generate energy, right? Okay, so here's the idea. So when he discovered this, he noticed a few things here. So I'm going to go through them each, and then I'm going to once we kind of like go with the new quantum theory of what's actually happening here, I'm going to come back and explain some of these more in detail. But here's what he noticed. So he said, so number one, a substance shows a photoelectric effect only if the incident light has a frequency above a certain threshold value known as the threshold frequency. So what this means is that if you get zinc, for example, it will emit electrons for violet light, but nothing for blue light. So the frequency of the light that was coming in, right? And remember, frequency and wavelength are like tied together. So like the type of wave that's coming in has to be a high enough energy or else nothing happens, right? And it goes like nothing happens, nothing happens, nothing happens. And then once you get to that certain frequency, then it starts shooting off electrons. Okay, so that was the first thing you noticed. And then number two is kind of the same thing. It says a frequency below that threshold value won't produce anything. Okay, so it's kind of the same thing there. Number three, different metal surfaces have different threshold frequencies. So it would take a different wavelength or a different frequency of light to start those electrons jumping off the plate, right? So it depends on what type of plate you were actually using. Number four, he said once the external light is at or above the minimum threshold frequency, that's right when the photoelectric current flow is instantaneous. So it's just snap of your fingers, that's when it starts happening, right? Number five, increasing the frequency of the incident light does not affect the photoelectric current flow. Okay, so what does that mean? So that means that if I change this light from, let's say, like blue light to green light, or like even ultraviolet light or something like that, that's actually not affecting the current that I'm reading on my ammeter there, or like that's just for measuring current, right? That doesn't actually affect how much current I actually have. Okay, which is kind of strange. You think the more and more energy that these little light waves have coming in, you would think that that would mean the more and more current that would be making it to the other plate, but it's not. Okay. Number 6, though, says increasing the intensity of the external light, so using a brighter light source, caused an increase in the amount of photoelectric current. So what that means is that, so if I, like in the last one I just said there, if I increase the amount of energy that those waves have, right, by making it a higher frequency, that doesn't cause more current. But if I send more waves at it, that's essentially what intensity means, right? If you have a really intense light, that just means that you've got lots and lots of wavelengths. There's lots and lots of waves that are coming at this thing. So if I increase the number of waves coming at this thing, then I start increasing the number of electrons that are jumping off the plate. Okay, so that was the next thing he found. And then finally, he discovered that increasing the external light source's frequency caused the kinetic energy of the photoelectrons to increase. All right, so what that means is that if he changed this thing from a certain wavelength of light or a certain frequency of light to, let's say like a higher frequency of light, then it didn't cause more electrons to jump off, right? It didn't cause more current, but it did cause every one of these electrons that jumped off to have a higher kinetic energy, right? It caused them to have more speed, right? They came off with more speed when it had a higher frequency. All right, so that's all kind of like the pieces of the puzzle here. And now we're going to try to put it together, like what's actually going on. Okay, so in this paragraph here, we're talking how classical physics point of view, it doesn't really explain this, and here's why. Because if we had even like a really low frequency of light, let's say that this was like red light, right? So let's say you had like a red light wave coming in. Well, if what's happening here is you've got these electrons that are stuck on the plate and they just need to be freed from it, and according to classical physics, if I just vibrate those enough, if I just like start them like shaking enough, they'll shake right off of the plate. So according to classical physics, if I sent in enough waves, right, even like with low energy waves, those things should really, like, more and more waves I sent, that should like end up loosening more and more electrons off of this thing. But that's not what happens, right? Like it's all this stuff that we have below that happens, right? So it doesn't seem like classical physics is actually explaining this properly. So it's gonna take a quantum physics approach to explain what's actually happening there, and it's gonna take Albert Einstein. This is one of his big works, right? He actually ended up winning the Nobel Prize for his work in this. Okay, so this is like an optional reading on Albert Einstein. I think everyone should know a bit about Albert Einstein, just everything he contributed. So yeah, please read through this when we're done, but I'm gonna, for the sake of time, skip on to the next part. So Einstein and the photoelectric effect. So here, if you remember from last lesson there, right, we were learning with Planck that it seems that energy and even light itself is quantized, right? It comes in those little like wave packets, and it's helpful to think that way, where if the idea of a photon, if you remember, was like a little bundle of waves, and we have to think about it as being like these little wave packets, right? And those are called photons. So you have an individual photon, right? You've got a thing there now. It's not just like a spread out wave like we were thinking before. It's actually these little packets of light, right? And this is where the change in thinking's got to happen, is that light itself is a particle. And once we start thinking in that way, we can start to explain the photoelectric effect. Okay, so Einstein was saying that there is a specific amount of energy that it takes to release the electron from the plate, and he called that amount of energy the work function. All right, so and I think this will help actually just with a picture is probably the best way to explain what's going on here. So here's what he figured, that you've got this electron that is bound to the plate, right? So here's our plate, and there's a certain amount of energy that's binding this electron to the plate, right? And that's really the same amount of energy that's binding the electron to the atom, right? It's the same type of thing. So it's got a bunch of energy holding it down, and then we send a wave packet, right? You can think about this as being like just a one wave packet coming in toward this electron. And if, let's say, this photon had exactly the amount of energy that was holding this thing down, had the exact amount of energy as the work function, then it would free the electron, right? The electron would leave. Okay, so, but if I send in more energy, right? So let's say I change that to like, a higher frequency or shorter wavelength light packet, and it comes in, well, then there's going to be like extra energy, right? This thing has more energy than required to release this electron from the plate. So that extra energy all ends up in the kinetic energy that the electron has when it leaves. So we get a higher kinetic energy, a higher speed of the electron when it comes off. And that's essentially it. So here's the equation that you can think of that really just is explaining this, right? So the kinetic energy of the electron, so that would be, this EK, right? The kinetic energy of the electron is equal to the energy of the photon. So energy of the photon minus the amount of energy it takes, so the work and it takes to release the electron, right? You could also think about, like, you could rearrange that too, right? And say that the energy of the photon is equal to the energy of, or the kinetic energy of the electron plus the work function, right? So we've done this a lot in like physics 20, where you got your energy before, right? That'd be the energy of your photon before is equal to, and then your energy after would be your energy of your electron, and then, plus the energy required to remove this thing. It's almost like your friction, right? When we did like our conservation of energy questions, how there was like the potential energy before and the kinetic energy after, but you had to like subtract the friction, like the work due to friction. It's almost like the same thing. This is just like the work due to the electron trying to hold on. Okay, so this really is the big idea, right? This picture right here, if you guys can understand this picture, it's going to really help when you're doing your calculations below. Okay, so anyway, now that we're looking at this and we have like an idea of what's going on, our experiment, or our findings, Hertz findings, make a lot more sense, right? So he said that increasing, yeah, so anyway, the idea here, if I'm shining light on this thing, right, then nothing happens, and then once you get to a certain frequency, they start leaving. Well, what you can think of here is that you've got these little wave packets, right, that are coming in, and you've got these little electrons that are sitting on there with a certain amount of energy that it takes to get them off. If I end up getting the perfect, like the right wavelength or the right frequency photon coming in, so the work function, then that photon, this one individual photon, is going to make this one individual electron jump off. But that's it. It's like a 1-for-1 ratio. One photon gives you one electron jumping off, right? So that makes sense. So if this is smaller than the energy required, then nothing happens, right? No electron jumps off. So it also makes sense here now that increasing the amount of energy that any individual photon has, right? So if I increase the energy of this photon, it doesn't matter, because it's still just going to come down to one photon for one electron. I can give this thing like a crazy amount of energy. That's not going to make more electrons going to come off. It's only going to make one come off. But it will, like if I give this thing a crazy amount of energy, that's going to make this electron jump off really fast, right? It's going to have a super amount of energy coming off of this thing. So that explains our findings here, right? So you've got increased frequency doesn't affect the current flow, right? Current flow is the amount of electrons that are actually coming, right? That's what current is. How many electrons actually get to that side of the plate? That's what current is, right? So it doesn't change. The more and more, like the higher frequency wave I give it, that doesn't change the number of electrons coming, right? So that doesn't, it's not going to increase, where was that? It's not going to increase the current flow, right? But if I increase the intensity, okay, so intensity, what intensity means is that we're going to have more and more wave packets, right? You've got tons and tons of these wave packets coming in. So that's going to make more and more electrons jumping off. So that will increase your current flow. Okay, so that's the idea there. Oh, and then lastly, this makes sense too, that if you increase your frequency, like so higher and higher energy wave packets, then that's going to increase the kinetic energy. That's going to give your like these electrons more and more speed, right? Okay, hopefully that makes sense. That is definitely the like the theory behind this. You need to understand why the photoelectric effect works now, right? So that's the theory part of this. All right, so now the calculation part of it. Well, actually, I'm sorry, we got one more experiment to go through. So Einstein was a great theoretician. Actually, he was a great mathematician too, right? But he didn't do his experiments, right? Like he didn't create his experiments to test his findings. So it came down again. So you guys have heard this name a few times too, Millikan. So Millikan came up with another experiment to test Einstein's theory now. And this actually ended up winning Millikan the Nobel Prize in physics as well for this experiment. Actually, this experiment and his oil drop experiment that we did in other lessons. Okay, so here's what it is. Looks super confusing, but for the most part, if you guys are trying to like memorize or figure out what's happening in this experiment, you could probably kind of like ignore most of like the stuff happening down here. This is all just kind of like meant so that he can turn the dial like up and down to get like the voltage that he wants. But here's the idea. You've got these light rays shining in here in a cathode ray tube, right? So just like before. But then he set it up so that he could have a negative voltage. And what I mean by that is that if he made it so that there's negative plates on this side, positive plates on that side, so that when the light shines onto the positive plates, then we get a photoelectric. Jump across from one side to the other, okay? But then what will happen is he turns the voltage up, right? So these negative electrons that have been released from this positive will be shot to the right here, but then they're going to be met with another electric field, right? The electrons are going to be like stopped. So he would turn up the voltage up until the point where he wasn't reading any more current, right? Because once he wasn't reading any more current, that meant that he had brought these electrons to a stop, right? And this is actually called the stopping voltage. And this is what it was, right? So he said the kinetic energy of an electron is equal to the charge of the electron times the stopping voltage, right? So in this way, he was able to figure out how much energy did these electrons have when they left the plate. So this was a main piece of the puzzle that was missing. So this is what the experiment was able to figure out, right? So that was really like in this question up here, he was figuring out how much kinetic energy does this thing actually have, right? So he was able to actually figure this out experimentally now, which was kind of a big deal. All right, so here's what he found too. He found when he started plotting his data for this one is that his equation actually looked like the equation of a line. So y is equal to mx plus b, right? Right back to math 10, where m is your slope and b is your y-intercept. So his equation took that form. So when he started plotting it with ek, right? Ek would be like my y-axis, and then f, like the frequency, would be my x-axis. So what that would mean, if it actually does follow our equation of a line, then h, right? That should be the slope of the line, right? That should be Planck's constant. And w, well, that should be our work function, right? And this is just using the equation that we had above. So when he did that, so he plotted all of this, and he found that actually is what the case is. So the work function would be the amount of energy required to make this thing jump off the plate, right? So that would be, this is like a negative energy, which makes sense. That's like the binding energy on the plate. So that'd be my, I should say, like, yeah, W, negative W, your work function there. Okay. And then he also found that his x-axis, right, so right there where it crossed, that was the threshold frequency. So just as a little context here, his data wouldn't have looked like this, right? It would have looked like this, where he just had, you know, a line that would start at the x-axis and then go up from there, right? And the different materials that he would use would have a different starting point, right? Maybe this one, the threshold frequency would be a little higher, so it would start there. Maybe a different material would be a little lower, and it would be over there, right? So all of this stuff below the line was just like extending the line downward, right? When he was doing the experiment, when he was plotting it on the graph. Okay. All right. So I just kind of drew the same thing I just did above, but okay, so this is what he found, right? That as he changed the materials, every one of these lines is just like a different material that he used, right? So they all had exactly the same slope, which makes sense. They all have Planck's constant as the slope, which is pretty amazing actually, right? Because we had Planck that came up with Planck's constant, right, from the last lesson there, using black body radiation, came up with a number that made sense, right? And then doing a completely different experiment, finding the exact same number, right? Finding that the slope of these lines that he was plotting was that exact same number. That's good evidence that they're onto something, right? When you have two completely different experiments that end up giving you, like with very high accuracy, like the same number, right? That's a really good indication that they're on the right track when they're doing this, right? Okay, so here's some examples, but we'll do one below here. So yeah, this is just kind of talking about how different materials or different metals have different work functions, right? The amount of energy. This is measured in electron volts. It doesn't need to be though, right? It could be in joules or whatever. Okay, so practice problems. All right. So number one, so it says if the threshold frequency required for photoelectric emission is 400 terahertz, what's the work function? Okay, so what do we know? So let's write down, so we've got F, so the frequency, but it's actually going to go by slightly different form. It's going to be F naught or F 0, right? Is kind of the way you say that. And it's written that way in your formula sheet as well. So F naught, or the threshold frequency, equal to, and it's 400 terahertz. So remember, you guys have that on your formula sheet. Oh, can't really hear me very well. Can you guys hear me now? Here, one sec. Okay, so your threshold frequency, so 400, and then terahertz. So terahertz, it's on your formula. Oh, let me say that. It's on your formula sheet. Is times 10 to the 12. Okay, so it's times 10 to the 12. Okay. Now, the next one that is also on your formula sheet that'll be new for you guys is the work function. This should be W. W is equal to Planck's constant times the threshold frequency. Okay, so that's pretty straightforward, right? So we can just plug that right in. So the work function is equal to, so H is Planck's constant, which is 6.63 times 10 to the negative 34. Oh. Joules times seconds. And then our threshold frequency there. So 400 times 10 to the 12 hertz. Okay. So that will be 2.65 times 10 to the negative 19 joules. Okay. So that's the amount of energy required to remove this electron from the plate. Okay. Now B says, if the surface is illuminated by light with a wavelength of 500 nanometers, what is the speed of the escaping electrons? Now, when I do these questions, I actually think it's helpful to like draw a little picture. So what's going on here? So you've got your plate, you've got your electron, you've got your wave coming in, right? Your wave packet. And then this electron is going to escape. So before we had the energy of the photon, right? That was the energy coming in, and that's the energy associated with my 500 nanometers, right? So energy of the photon coming in, and then you've got your energy of your electron going out. Okay, so that's like energy before, this is energy after, but then we've also got the work function, right? The energy required to get that electron to leave. So this one's not on your formula sheet. You guys need to be able to come up with this one. So energy before, so I'm going to say energy of the photon is equal to the energy of the electron, so EK right after, plus the amount of energy for the electron to leave the plate, or the work function. Okay, so that's my equation to begin with. That's my starting point. And it wants to know what is the speed. Okay, well, speed, I know EK is 1/2 mv squared, right? So I can just solve for that here. So let's work our way down. So the energy of a photon is h times the speed of light over wavelength. That's on your formula sheet. That was from last lesson, right? Is equal to, and you know what? I could split this one up into 1/2 mv squared and solve for v, like right out of this equation. But I already know where we're going with this. I actually kind of want to know what the kinetic energy is, because I'm going to use it in the question below, right? So I'm going to do this in 2 steps. I'm going to find the kinetic energy of the electron, and then use that to find my speed. That'll probably actually be a little easier for the algebra here too. So I'm going to leave this for now as kinetic energy, and then plus my work function. Okay, so then just subtract the work function from both sides. So we're going to have Planck's constant times c over wavelength is minus W is equal to the kinetic energy of the electron. Okay, and then just filling that in, our Planck's constant is 6.63 times 10 to the negative 34 joules times seconds. And then the speed of light is 3 times 10 to the 8 meters per second over, and then they gave us the wavelength, right? So it's going to be 500, and then nanometers is times 10 to the negative 9. So 500 times 10 to the negative 9 meters. And then all of that minus my work function from above, right? So that was that 2.65 times 10 to the negative 19 joules. And that's equal to the kinetic energy. All right, so what do we get there? I don't actually know yet, so give me a second. I got to type this in too. 6.63. Almost there. All right, so I end up getting a kinetic energy of 1.328 times 10 to the negative 19 joules. Sorry for the bad writing there. Okay, so now that's Now that we know that, we can figure out the speed of the electron by just using the simple formula EK is equal to 1/2 mv squared, and just solving for v here. So rearranging this, we get 2EK over m, and then take the square root is equal to v. So we're going to have 2 times the number we just found there, so 1.328 times 10 to the negative 19 joules, divided by, now what mass am I talking about here? Well, remember, we're talking about electrons. It's electrons that are moving. So this will be that, again, on your formula sheet, 9.11 times 10 to the negative 31 kilograms. Okay, and then take the square root of all of that. So we end up with, I'm going to cheat, 5.4. So that was V. So we get 5.4 times 10, 5.40 times 10 to the 5 meters per second. Okay. So now, what's the stopping voltage? So now you guys are going to be happy that we found EK as part, like in the middle step there, because stopping voltage, and this one is on your formula sheet under atomic physics, is EK, and it's written as EK max, is equal to the charge of an electron times the stopping voltage, right? That is Millikan's equation from above, right? So now so the stopping voltage for the photoelectrons is just going to be EK over the charge of an electron. So we just this number that we found from before divided by the charge of electrons. So that's going to be 1.328 times 10 to the negative 19 joules divided by, now the charge of an electron is 1.6 times 10 to the negative 19. Okay, so if we do that, we end up with, and again, I'm going to cheat, 0.8. You know what? I think I get 0.83 volts. But the reason I think that I get that is I rounded this. I used this in my equation, and I shouldn't have rounded that yet, right? Like I ended up using that number right here. So I'm not quite as accurate. So if I was doing this, to be like perfectly accurate, that's where I made my mistake. I should have used all the digits in that one as well. But so if you did that, you would have ended up getting the same answer as this one. Okay, so that's it.